Hello everyone. This video is dedicated to tying everything discussed in the course into a comprehensive design example. The example that we will be using to illustrate the entire computer-aided engineering process is the design of a toy arch bridge for children. The problem parameters that will drive part parameters are user requirements, and the conforming requirements that allow us to sell this arch bridge as part of a set of building toys. The first step in C.A.E. is completing computer-aided design, or CAD. During this step, we will be able to make, combine, and size the features needed to make the arch bridge geometry. This will also allow us to define the relevant part parameters, and establish relationships between part parameters and the problem parameters. Our first step in CAD is to figure out how to create an arch bridge using feature-based modeling. Deconstructing the toy arch bridge, the bridge is composed of a rectangular prism and an elliptical cylinder. With these geometries defined, we also now have their characteristic equations, and we can generate the defining topological sets of nodes and edges. The next step is to complete the Boolean-based modeling to put the features together. Recalling the video on Boolean-based modeling, we know that we would need to subtract the elliptical cylinder from the rectangular prism. You can adjust the node and edge sets to center the elliptical cylinder in the horizontal direction, and place the horizontal elliptical cross-section diameter on the bottom edge of the rectangular prism. This process can be completed using a variety of CAD mating techniques, which will not be discussed further here. The final step involved in CAD is part parameterization. This is where we analyze the problem parameters and figure out which translates to optimizable part parameters and which part parameters must stay fixed. Let us say, for example, that the total height, h, and width of the part, w, have been predefined by dimensions of other toys in the set and customer requirements. This means that the only parameters that we are allowed to optimize are the length of the overall bridge, L, and the parameters that are intrinsic to the subtracted elliptical cylinder, the horizontal radius of the elliptical cylinder cross-section, RH, and the vertical radius, RV. With the parameters defined and arbitrarily sized, for now, we have completed computer-aided design and can now move on to computer-assisted optimization, or CAO. Before continuing on to CAO, it is worth noting that the predefined constant part parameters could have been calculated via sensitive parameter control, where different manufacturing, packaging, or supply chain parameters impacted these part dimensions in nonlinear, complicated ways. Pareto optimization may have been used to derive the constant parameters as a result. Now, let us discuss CAO. The first step of CAO is setting the objective function of the problem that will need to be optimized. In our case, this function will be defined by the costs for materials and then the costs of manufacture. This objective function will be functions of the cost of the original material stock size, the material removed, and the methods of machining, which will all be functions of the fixed part parameters W and H, and the optimizable part parameters L, RV, and RH. Once this has occurred, the next step is to complete continuous and discrete optimization. First, let us consider discrete optimization for the perspective of available stock material. Let us say that we can machine our bridge from a pre-cut swath of material. There are a few different sizes and shapes from which we can start to create a final design. Each starting amount of material would cost a certain amount of money and would need certain amounts of machining to create the final product. The cost of the material size is the optimizable discrete point, and the material machining and removal would be part of the continuous optimization. The next step in CAO is to define constraints and/or penalty terms. Let us first look at constraints developed based on the features. Based on the interaction of the rectangular prism and the elliptical cylinder, we want the vertical radius of the elliptical cylinder cross-section, RV, to be less than the height of the rectangular prism, H. Likewise, we want the horizontal diameter of the ellipse, or 2RH, to be smaller than the length, L. With these constraints defined, let us look at the requirements from the problem parameters. Let us say that for reasons related to required product durability, stress requirements, and aesthetics, we know that the different surface areas and the overall product volume need to conform to certain ranges of connected values. We would need to convert these different ranges into functions of our original optimizable parameters, L, RV, and RH. With these intact, we have now defined our constraints for constrained optimization. The final step in CAO is the discussion of deterministic or stochastic optimization. Depending on the application in mind, sometimes it is unnecessary to complete stochastic optimization, as using a safety factor would suffice. However, in a situation like this where you would be manufacturing a large quantity of parts, it makes sense to complete stochastic optimization to cover all the sources of error, thereby becoming more cost-effective. After all, stochastic optimization allows us to include the possibility of material defects or manufacturing errors. By the central limit theorem, with enough data points available, the likelihood of errors impacting any constraints or parameters allows us to convert the constraints/parameters into functions of normal distributions. From there, we can operate onwards to optimize everything while minimizing any failure due to the aforementioned errors. With CAD and CAO both now complete, we keep on iterating until all our convergence criteria are reached. The convergence criteria can also be restricted further to ensure a more optimal solution. However, the stricter the convergence criteria, the more iterations needed to converge. This leads back to using the law of diminishing returns to determine when further optimality would be worth the calculation requirements. As you can see, completing C.A.E. for even a simple problem like this one can easily become very cumbersome. It is only feasible to optimize in this way because we were able to limit the number of applicable parameters and simplify the manufacturing process. Imagine a much more involved problem that would involve even more optimizable part parameters with a lot of potential uncertainties. In the event of situations like this, it can become impossible to solve the optimization problem analytically. As a result, you would need to use your constraints and uncertainties to define the ranges that parameters can take on, and run a Monte Carlo simulation to get an optimal design. With that, this completes the course on generative design and optimization. My name is Abhishek Ram, and I am a recent graduate of mechanical engineering from the University of Massachusetts Amherst. With the rise of scientific computing and mathematical modeling, it is becoming more vital for engineers of all types to be able to understand some basic tenets of computer-aided design, modeling, and engineering. As a result, I developed this course to offer an introduction to these topics at a level such that even high school students could comprehend and follow along. By introducing these first principles early on, the goal is to help improve young engineers' understandings of how to use the computer properly to aid in design and engineering. If you would like to provide feedback, suggest more video ideas, or connect, I have posted my LinkedIn and personal website in the video description. Thank you for watching this video and these videos, and I hope you have a great day.